Hello, everybody. I'd like to start this week by talking a little bit more about the difference between covalent and ionic bonds. So we know now that the electrons in a covalent bond are shared by both atoms that are being bound. So that electron would have just an equal probability of being around one atom as it would be in the other atom that's in that bond. The electrons in an ionic bond are largely associated with one of the bound atoms. So in that scenario, it's like an electron was given from one atom that's being bound to the other one. And that electron's only going to associate mostly just with the one that received it. Whether a covalent or ionic bond is formed is determined by the electronegativity of the binding atoms. What is electronegativity? Electronegativity is the tendency of an atom to attract a bound electron. So the question then becomes, how do I know what the electronegativity of any given atom is? And this is just a thing that we've actually calculated out. And you have this periodic table here that tells you the electronegativity of all the different elements. And you'll notice a general trend where as we move left to right, there's increasing electronegativity, which makes sense because we know that these guys over here tend to want to take on a negative charge. They want to get electrons. Over here, where we tend to see positive charges, they want to give up an electron. You also see that electronegativity decreases as you go down the periodic table, and that's because these heavier elements here have a lot of electrons, and there's just less of an effect when they take on a new electron. It kind of gets diluted down in a process known as electronic shielding. So as we said, whether or not we wind up with a covalent or an ionic bond depends on the difference in the electronegativity between two elements. So if this is the electronegativity of one of our elements, we're going to subtract the electronegativity of the other element, and then we're going to put them in these brackets here that indicate that we're going to have the absolute value, or we're going to take the positive if it's negative, and we're going to take the positive if it's positive. So once we calculate the change in electronegativity, the difference between them, we're going to have some little bins that we're going to put them into. So this kind of does indicate that bonding occurs on a spectrum, right? We can have all kinds of different kinds of bonds, but we love to put things in little bins as human beings, and so that's what we're going to do. So if we see that the difference is less than 0.4, we're going to call that a pure covalent bond. If the difference is 0.4 to 0.8, we're going to call that a polar covalent bond. And what this means here, when we say polar, is the electrons aren't going to be completely distributed through the bond. There's not an equal likelihood of it being on either one, but it does spend a significant amount of time with one, and it spends kind of the majority of its time on another atom, but it's not so one-sided that we would call it an ionic bond. So when we have a greater than 1.8 difference, we're going to call it ionic, indicating that that electron is pretty much always staying with one of the atoms. Let's take a look at an example here. If we have a carbon-carbon bond and we go back to our table, we'll see that the electronegativity of carbon is 2.5. So we can calculate the difference as 2.5 minus 2.5, which is obviously 0. And this is a pure covalent bond. So if we have the same atom, it would make sense to have a pure covalent bond, because why would it necessarily associate with one over the other? There's an equal likelihood. If we look at something like sodium fluoride, we'll find that the electronegativity of sodium is 0.9, and the electronegativity of fluoride is 4.0. Fluoride is actually the highest electronegativity, most electronegative of all elements. When we do that subtraction, we get negative 3.1, and we're doing the absolute value, so that's going to be 3.1. 3.1 is greater than 1.8, and so therefore this is an ionic bond. Now I'd like to look at the case of polar covalent bonds. So if we look at a bond like a molecule like HCl, hydrochloric acid, we have hydrogen and chlorine. We can calculate the difference in their electronegativity, and we get a value of 0.9. And that's going to fall between 0.4 and 1.8. And so that's going to be a polar covalent bond. And what the consequence of that is that the electrons in this bond are going to want to sort of associate with chlorine a little bit more, okay, than it will with the hydrogen. And that's going to lead to a partial negative charge on here. And we signify that with this lowercase delta. It's a Greek letter. And then it's going to lead to a partial positive charge on the hydrogen. And this separation of charge is going to lead to what is known as a dipole moment. And the dipole moment, you can think of it like a little electrostatic magnet sort of thing. So it's saying that it's going to draw electrons from where it's sourced to where the arrow is pointing. And then we usually put this little horizontal line in here to indicate that we're talking about a dipole moment, as opposed to like a bond or a reaction arrow. So if we look at OH bonding and we do the difference in electronegativity, we get 1.4. We see that that's a polar covalent bond. And then if we extrapolate that out to water, we're going to see that the hydrogen is going to be pushing towards the oxygen, and the hydrogen is going to be pushing towards the oxygen here. These are going to be our bond dipole moments. But what winds up happening is they add together to give us the overall dipole moment of this molecule. So the question becomes, how do you add arrows? And these arrows indicate what mathematically is called a vector. And the way that you add vectors together is you just put them head to tails. Okay, so if you imagine moving this one over here and moving this one over here, and now we have it such that we start from someplace, we have the arrow going here, it's where it's the next one's starting, we take the arrow here, right? And then we draw a line from where the first one started to where the last one ends. That's going to be the new dipole moment. So if you move this arrow over to here, you can see that the dipole moment, when we've added them together for the overall water molecule, is pointing up through the oxygen in this way. So this oxygen is going to be attracted to positive charges, and these hydrogens are going to be attracted to negative charges. So we could draw on here our delta values. To give us a sense of the charge on each one of these guys. So I want to talk now about some of the other configurations and what that has an effect on the overall dipole moment of a molecule. So first I want to start off here with carbon dioxide. This is a linear molecule. It's just in this straight line here. And we can see here that the bond dipoles are pulling at one another in opposite directions with equal magnitude. And if we add those together, we're going to wind up getting no dipole for the overall carbon dioxide. So even though it does have bond dipole moments, it has no overall dipole moment. Here we have a case of magnesium being bound to iodine and being bound to fluorine. We know fluorine is the most electronegative element, and iodine is further down the periodic table. So we wind up getting opposing dipoles where one is going to be a little bit smaller than the other one. And when we're done matching those up to one another, we wind up with a net dipole moment that points towards fluorine but is smaller than either of the bond dipole moments. Here we have the case of boron trifluoride. Boron is a flat triangular molecule, and we're going to see that we have these bonds pointing out towards our fluorines in each case. If we move them all over here, head to tails, we're going to see if we start here, we're going to go here, here, and we're going to wind up back where we started. And that indicates that, again, there's going to be no dipole moment for this molecule. Here we have carbon tetrachloride. And I want to show you guys this little model right here. So this is what is trying to be represented by drawings that look like this. So the scenario is kind of like this, where we have the top and the side one in the plane of the paper. We have the one that I'm holding right here that's facing out of the paper, and there's that guy in the back that's facing into the paper. And this shape is pretty special. It's called a tetrahedron. It's one of the platonic solids, and they tend to pop up a lot, this shape and other platonic solids in chemistry. They're special because they're the only shapes you can make where every one of the sides, if I pictured like those three being joined together and making a face, all the faces would be the same shape and the same size. So in this scenario, we have all our dipole moments facing out towards the chlorines. And I'm not going to attempt to draw it because I can't really do it that well. But in this scenario, you still wind up with no overall dipole moment around that molecule. So now I want to take a moment to talk about the dipole moment and electric fields. So the strength of a dipole moment has to do with the charge that's in each one of these guys and the distance that they are from one another. So you see, you increase the distance or you increase the charge, you increase the overall dipole moment. And when we apply an external electric field, which could be done by taking a metal plate with negative charges on it, and a metal plate over here with positive charges on it, that's going to create an external electric field. And what's going to wind up happening is that the dipole moments, when they're allowed to, if they're in the liquid or gas state, are going to arrange themselves to these fields. So rather than just being randomly pointing wherever like it normally would be, it's going to arrange itself such that the dipole moment points towards the positive plate. And we can see if we rewrite our water molecule like this, you can see the negative is closer to the positive and the positives are closer to the negative.